So in a previous video, we concluded that acceleration is associated with a space-time curvature. And what we'll do here is to illustrate the equivalence principle, which suggests that acceleration and gravity have an accelerated system and a system in which there's a gravitational field share properties, and therefore we will conclude from the equivalence principle that gravity is space-time curvature. Okay, so to do this, let's imagine a reference system that is freely falling. So here is a flat, and for simplicity, let's just make it an infinite Earth, completely flat, so the gravitational field is perfectly vertical, and you are in a freely falling room or laboratory, and so here you are accelerating downwards at g, and so this is you in your lab, and you have you release here's an apple there, and it's also freely falling, and then let's say we have another apple over here, and the way these objects move with respect to you is such that they remain in those positions. they're all if you release them at rest with respect to you, they will remain at rest with respect to you, because everything is falling at g, including the laboratory. So the idea is that this is analogous to removing the Earth and just imagining your laboratory being in free space. If you release the two apples next to you, right, everything will be moving at the same rate. In other words, zero acceleration, actually. You'll just be sitting there, but from your perspective inside the laboratory, you won't notice any difference. Everything inside behaves exactly the same in these two cases. So, in a sense, motion, if you allow yourself to free fall, you allow yourself to respond to the gravitational field by freely falling. It's analogous. What you experience inside your laboratory is analogous to a situation where there's an absence of forces. So now let's imagine that you don't allow yourself to free fall, but you are on this infinite Earth, and here's your laboratory. So you're just sitting there. You don't free fall, and so you are subjecting yourself to a force, the normal force, so that you don't fall through the surface here, and then you release your two apples. Of course, they will accelerate downward at g, and that's a very different situation compared to here. And the idea is that this is analogous to you actually getting into a spaceship or being in a laboratory that's in free space like this, except now you have to put a rocket underneath your laboratory and fire away at an acceleration of g. Of course, the idea here is that there's a force, F equals ma, and so the force is such that it generates an acceleration that's g in this case. And in this situation, you will feel exactly the same thing as you do in this case with your apples, if you release them in such a system, they will accelerate downwards exactly like they do here at a rate of g. And so not letting yourself be pulled by gravity is analogous to a force acting on your system. And so we're concluding that acceleration and gravity are very similar. And so gravity is, in some sense, what we call space-time curvature. That's the message of this principle of equivalence.